In this video, we're going to overview some of the basic features and usage of the scdbg tool. This is an adaptation of the libemu sc test project to add more hooks, more easily human-readable output, and some other features that we'll be covering. You can get to the help screen just by typing in scdbg-h. That's going to dump all the options for you. This one, we can see the compile date is July 21st. And I'm not going to go through all of these here, just so you know that they exist. To get started, we'll go through a very simple example. I will do scdebug-f, which tells it to load a file, and we're going to start with download.sc. This is the most minimal command line that you can use when trying to run a shellcode. We see that it started to load up. The default options are it sets the max steps and the base offset. Both of those you can adjust. And here we can see load library, get temp path, URL download, and when execute. So basically we know everything that this did. Also, if you want to take a quick look at your shellcode, you can use the dump option and it'll just print out a hex dump for you. Here you can see that nops, calls, and jumps, EB, E9, and E8 are all highlighted for you. This is in case the shellcode started somewhere in the middle of the file and you had to figure out where the beginning was. Also, there is a find SC option, and it'll go through. It's kind of brute forcing the file right now to determine the step counts. And here it found two possible start offsets, 0 or 15. And you enter the index, the 0 or the 1, in order to determine which one. If the final EIP had been an API address, it would have shown what the API address name was. If you run it in auto mode, it will automatically select the first one in this list in case you were doing an automated batch run. And that's used for the directory option, where it can scan an entire directory of shellcodes. So here, I'll just hit return, which will default to 0, and it'll run the shellcode again for us. Also, if you wanted to dump it, well, let's say we wanted to disassemble it to see what the instructions were. We could say we want the first 20 instructions. So here we're disassembling 20, and it'll show us our beginning of an output. That's all very basic usage stuff. To get a little bit more complex, I suppose the next example worth looking at is probably one that writes a file to disk. So we'll do scdebug-f drops.sc, and first we'll just see what this one wants to do. So here we see that it's creating a com file in the temp directory, it's writing it, and then it's going to execute it. Now, if we wanted to actually capture that file, what we could do is we could go into interactive mode with the /i switch. And we're also going to use the /temp to override the default. If we don't use the temp command line, it will use the temporary directory on the system to drop the files under random file names. I'm going to override that just for convenience so that it goes to our current directory. All right, so here we see our interactive mode has been enabled. It tells us what our local file is, and we control, scdebug uses random file names so that the shellcode does not control the file name ever. And S9, here it is. Here's our temp file created in there. We can look at it, and you don't see the MZ headers because this one literally is a com file. This is an old school screensaver that it's dropping to execute as just a demo shellcode. Let's see, another one that we might want to check out. Now we're starting to get into kind of some of the more advanced features. If we wanted to, let's see, we'll take a look at one that uses SEH, structured exception handling. scdebug has added support for this, and this is what it looks like. We can see that an exception was caught, and then it goes into its main shellcode. Here we see we're getting an error at the end. In this case, it's actually because our map viewer file was failing because it's doing a download, and then it's trying to open that download. And we didn't use the fopen option to have it open a handle to that file. So of course it's going to run into errors because we're not replicating the entire environment. A scdebug will work with shellcode that opens file handles, and we'll look at that in just a second. Let's see, if an example of that would be, I'll do the fopen example. Let's see. Now get the command line there. So here's a command line that I already have configured for it. I am going to first just run just the shellcode part, as in our other examples. And here we can see get file size, and the handle is incrementing, and it's actually hidden any more of these repetitive calls from us because otherwise it'd spam the terminal. And we can see that our step count ran out because our max steps is here. So in this example, it's scanning for an open file handle. The shellcode came from a Word document exploit. So what we need to do is we need to supply an open file handle for it. So here with the fopen option, we are going to supply the parent document. So now when it calls get file size and the handle is 4 or 8 or 1 or something low like that, and we know that it's a file handle scanner, it's going to automatically feed it the file handle that it opens. The -u option is unlimited steps so that we don't hit our step count. I is the interactive mode, and again, temp is for the temporary directory. So now we'll see what this one does. All right, we can see we got much farther in our shellcode now. Here it returned a valid file handle called create file mapping. So it's opening up the document. It's reading the document in. It's decoding data from the document. We can see with the set file pointer, read file, set file pointer again. So it's incrementing through different parts of the file and doing things, and it's creating temporary documents. Now, if we go here, here are our interactive mode files, and you can see that I actually ran this once before. 978 is our current run, and if we were to look at that in our hex editor, now we have an executable that was dropped to disk, and the other one is a Word document that was shown, that they used to hide the infection. So this works pretty good for those types of shellcodes. I use it a lot for that. Another example of kind of an advanced one like that is if we did. All right, here's another example of a shellcode, and on this one we have to do, let's see, I'll take out this CFO option because I'll describe that in a second. So we're running another one that uses the fopen. In this case, it was a download that was, so here we go, download to cache file, create file W, and when you see this path here, that is because this function automatically renames, it uses a temporary file name that it feeds back into a buffer. So it's opening that temp file path, and then it is decoding it and stuff. If we went here, if we went to our CFO folder and take a look at our executable, we can see it has the structure of an executable, but it's encoded. This isn't, I mean, this should be an MZ, and this program does not run in DOS mode. So it's obviously encoded. I'm going to get rid of these temporary files here. And in this case, what we need to do is, let's see, I'll run it one more time like that. All right, so S938, if we look at that, all right, a length of 0 bytes. So while temporary files were created, it wasn't quite right. And that's because it's not opening the right document. What we need to do is we need to override this create file to use our fopen handle, because this path right here does not exist. So we need to override it to use our fopen handle. And that can be done through the CFO option, which is create file override. It only overrides the first create file, and that's usually used in this type of shellcode. That's usually used for here, like a download. And then subsequent create files would be for writing the dropped file to disk, and you don't want to overwrite that. So it only overrides the first, and it's useful for this type of shellcode. It's kind of a hack, but it does work. So here we go again with the CFO option. Here we go. We got the S8T4, S8T4, and now we have our decoded executable. Some of the other types of shellcode that scdbg handles, that's kind of neat, or some of the other options rather, we'll do scdebug -f API table, table.sc, and we'll take a look at what this one does. All right, here we're not getting a whole lot of feedback. The shellcode crashes, there's an error in it. If we want a little bit more information, we can do -API, and what that's going to do is it's going to scan at the end of the run. It's going to scan for the API table if it can find it. And here we were able to get the full API table, so we have a bit of a better idea of what this shellcode does, or maybe what family it's from or what template it was made by. Also, there is -R report mode, which comes in quite handy. And that includes like a signature scanner. It includes memory lookups. So here's some of the more information that all of this is from the analysis report. We can see that it decodes itself in memory. We can get a memory dump if we wanted. Reads to DLL memory detected, tells us how it gets the kernel 32 base address. Sometimes it can detect the decoder. In this case, it detected the decoder and the XOR key right there. Signature count, it shows us the signatures that were found in here. This only has a very basic signature engine. And a memory monitor log. Another neat one to look at is, and we'll do report mode on that as well. So here we see that global alloc was called, then it copied code. Global alloc was called. Now we see code executing in that global alloc, so it copied the code over to that, and now it's executing in the memory buffer. Here it's getting the address of some API and calling virtual protect on it. And now we can see that like load library was called with an API address that's in the DLL memory. It's not within the shellcode memory. So it's using a fake return address to do this stuff. And we'll just skim down here real quick because we're getting towards the end of this video. We can see that in the memory monitor log that there were hook checks performed on these API. And we know that by how the DLL memory was accessed. And we know that there was API patching found. And we have the address that the API patching was found that did it. And we have the address that was patched. And in this case, it was looked up and it was found to be the address of unhandled exception filter in these API. So we're showing a lot of information here. And I guess these are just some of the basic features, well, even some of the advanced usage of scdebug. We'll also do one more real quick. And let's see, we'll do create thread.sc just to show how threads are handled. This will handle some process injection and some thread API. In this case, we see create thread was being called. So now we're transferring the execution to the thread start, and then we're able to continue. If this had been like a process injection shellcode, it would carry through and instead of open process and create remote thread, it would just execute it all within the same thing. So that makes the analysis a lot easier. In this case, we can see the crypto API is being called, and it's being used as part of a domain name generator, which is kind of neat for a shellcode to be doing. Just a couple other quick features.